The philosophical principle known as Occam's razor is one of the most widely cited and yet frequently misunderstood tools in the entire history of human thought. Its core intuition is deceptively simple. When presented with competing explanations for the same phenomenon, the simplest one is most likely to be true. However, this apparent simplicity belies a profound and nuanced concept that has shaped centuries of scientific inquiry, philosophical discourse, and even everyday reasoning. It is not a blunt instrument for dismissing complex ideas, but a refined guideline for navigating the path of rational inquiry and theoretical elegance. To truly understand its power, we must delve into its origins, its precise meaning, and its proper application across various fields. The principle is named after the 14th century English Franciscan friar and scholastic philosopher William of Occam. It is crucial to note that Occam did not invent the idea out of thin air. He was formalizing a strand of reasoning that can be traced back to Aristotle and other earlier thinkers. The term razor is a metaphor for its function. It is a tool for shaving away unnecessary assumptions, entities, or logical steps from a theory, leaving behind the most parsimonious and essential core. Occam himself expressed the principle in Latin in various ways, most famously as entia non sunt multiplicanda praeter necessitatem, which translates to entities are not to be multiplied beyond necessity. This original formulation highlights the razor's primary target: ontological commitments. It is a warning against populating our worldview with more things, forces, or categories than are strictly required to account for the evidence at hand. What, then, constitutes simplicity in this context? This is the heart of the matter. The razor does not advocate for the simplest explanation in an absolute or simplistic sense. It is not about the explanation that is easiest to understand or the one that requires the fewest words to describe. Rather, it prioritizes the explanation that makes the fewest new or ad hoc assumptions. A theory with a high degree of simplicity, or parsimony, is one that explains a wide range of phenomena using a small number of fundamental principles and entities. For instance, consider the transition from the Ptolemaic model of the universe to the Copernican one. The Ptolemaic system, with its Earth at the center, required a complex system of epicycles, deferents, and equants to explain the observed retrograde motion of planets. It was a patchwork of fixes added over centuries to make the model fit the data. Copernicus' heliocentric model, while revolutionary and initially counterintuitive, offered a far simpler explanation from a structural standpoint. The retrograde motion was naturally explained by the relative motions of Earth and the other planets orbiting the Sun, eliminating the need for many of the cumbersome geometrical constructs. The simpler explanation, in terms of foundational assumptions, proved to be the correct one. The power of Occam's razor lies in its deep connection to probability and epistemology. The fundamental reasoning is that each additional assumption in an explanation introduces a new point of potential failure. With every new entity or speculative cause we add, we multiply the probabilities that our theory is wrong. Think of it as a chain of reasoning. A chain with many links is more likely to have a weak or broken one than a chain with only a few, strong links. Therefore, a theory that requires fewer leaps of faith, fewer unverified entities, is statistically more likely to be true because it has fewer components that could be falsified by future evidence. This is not a guarantee of truth, but a guiding principle for hypothesis selection. It tells us which theory we should investigate first, which one has the prior probability in its favor. It is the logical embodiment of the idea that extraordinary claims require extraordinary evidence. A complex theory that posits unseen forces or entities is making an extraordinary claim. The razor places the burden of proof squarely on that theory to demonstrate why its additional complexity is necessary. In the realm of science, Occam's razor is not a formal law but an indispensable heuristic that operates at every level of the scientific method. Scientists constantly use it to choose between competing models. Isaac Newton's laws of motion and universal gravitation were triumphant in part because of their breathtaking parsimony. A single mathematical framework could explain the fall of an apple, the orbit of the moon, and the tides of the ocean. When a new particle is discovered in a particle accelerator, physicists will first seek to explain its properties within the existing standard model. It is only when the data becomes utterly inexplicable by the current paradigm that they will consider theories that propose new particles or forces. This conservative approach, guided by the razor, prevents science from descending into a chaos of infinite speculative entities every time a new, unexplained datum appears. It enforces a discipline of rigor and elegance, ensuring that complexity is only introduced when it is forced upon us by the evidence itself. However, the application of Occam's razor is fraught with potential misapplications and its utility has clear boundaries. The most common mistake is to confuse simplicity with simplisticness. The razor does not mean that the world itself is simple. Often, the universe reveals itself to be incredibly complex. The principle is a rule of thumb for constructing explanations, not a statement about the inherent nature of reality. Furthermore, the simplest explanation is always judged relative to the available evidence. If a simple explanation fails to account for all the data, while a more complex one accounts for it comprehensively, then the razor has been overruled by empirical necessity. The complex theory becomes the better explanation by virtue of its superior explanatory power. For example, the theory of evolution by natural selection is a complex theory with many mechanisms and a vast historical scope. Yet, it is overwhelmingly preferred over the simpler explanation of special creation because it accounts for millions of pieces of data from genetics, paleontology, and biogeography that the simpler theory cannot. The razor is subservient to evidence. It is a tool for choosing between theories that have equal explanatory power. When one theory explains more, it wins, even if it is more complex. The principle also extends far beyond the hard sciences into philosophy and everyday life. In the philosophy of mind, a classic debate revolves around the mind-body problem. Substance dualism, famously argued by René Descartes, posits two fundamental kinds of substance: physical matter and non-physical mind or soul. Materialism, on the other hand, argues that only physical substance exists and that consciousness is a product of physical processes in the brain. A materialist would wield Occam's razor against the dualist, arguing that the postulation of a separate, non-physical substance is an unnecessary multiplication of entities. Why invent a mysterious soul interacting with the brain in an unexplained way, when the gradual development and complexity of the physical brain itself seems to correlate perfectly with the development and states of consciousness? The materialist position is seen as more parsimonious. In daily life, we use the razor instinctively. If you come home to find a window broken and your valuables missing, the simplest explanation, a burglary, is almost certainly the correct one. The alternative, that a miniature meteorite precisely broke the window and a separate, unrelated poltergeist hid your jewelry, introduces a cascade of wildly improbable and unnecessary assumptions. The razor guides us toward the most plausible, common-sense conclusion. In the modern era, Occam's razor finds new relevance in fields like machine learning and statistics, where it is known as the principle of parsimony or regularization. Complex models with many parameters can easily overfit the data. This means they learn not only the underlying pattern but also the random noise in the training dataset. While such a model might perform perfectly on the data it was trained on, it will fail miserably when presented with new, unseen data because it has memorized the noise rather than learning the general rule. Simpler models, with fewer parameters, are less prone to this overfitting. They are forced to capture the essential, underlying trends in the data, which generalizes much better to new situations. Thus, the razor is not just a philosophical preference but a practical necessity for building robust and predictive algorithms. It is a formal mathematical defense against the seductive trap of unnecessary complexity. Ultimately, Occam's razor endures because it is a powerful embodiment of intellectual humility and efficiency. It counsels us to resist the temptation to invent elaborate, Rube Goldberg-esque explanations when straightforward ones are available. It is a procedural safeguard against the human propensity for superstition, conspiracy theorizing, and metaphysical extravagance. A conspiracy theory, for instance, often explains a set of events by positing a vast, hidden network of actors and a flawless cover-up, an explanation of immense complexity. The razor cuts this down, favoring the simpler explanation of institutional incompetence, individual error, or random chance. The true legacy of William of Occam's sharp insight is a lasting reminder that in our quest for truth, whether in science, philosophy, or daily life, the most elegant and economical path is very often the one that leads us to reality. It is a trusty compass for the rational mind, pointing toward explanations that are not just simple, but robust, testable, and profoundly connected to the world as it is.